Oh, how you guys doing today? Good? Perfect. So let's move on to the one we taught in chapter 5. Let's try to do a quick review on what we did on Monday. Either you watch on the YouTube channel or you're here. We talked about the thermochemistry. Thermochemistry. Okay. So literally, we're gonna talk about a lot of the heat energy. Or we express those sometimes in the terms of the enthalpy change. This is the term we're going to use precisely, not just the heat energy, but also including other types of energy happening in your chemical reaction. So we're going to do the thermochemistry here in chapter 5. We talked about the enthalpy, entropy, gives free energy and everything. But like I mentioned on Monday, we're going to focus on the enthalpy most of the time. So if that is the truth, let's try to look at the energy first. Okay, so energy simply means capacity to do work. Okay? So you have to have energy to do certain type of work. So what I mean by work is if you can have enough energy to do some removing or moving some matter into other position, we can define that as a work. So try to move something in another location, you need to have energy. That's what it means. Okay? So that means this type of energy, mainly we discuss in the kinetic energy and the potential energy. So I'll give you actually several examples for those two. So the kinetic energy is energy kind of caused by motion. Something that is moving that creates some energy, that's kinetic energy. So potential energy is the created energy because of some type of a structure or the arrangement of atoms. Or you can say the molecules were also inside of molecules, so the atoms or molecules. You can also think about the position of electron, the proton, the neutron. They're all in part of making a potential energy. So this might be the kind of hard to estimate. So we don't normally talk about this one, not too much. But so there's an example for those two. So kinetic energy, you can think about electronical energy. Another one is the heat energy. Okay? You can say thermal energy. Another one, the other one would be the light energy. Or you can call this the radiant energy because it radiates over space. Okay? Or you can say just light energy would be the okay. So this would be the kinetic energy because those are type of energy created by the motion of something. So if you think about the electrical energy, this is coming from some electrical charge motion that makes some electrical energy like in electricity. So you're going to have a certain motion of electrons or the protons. You're going to have electronical energy. You know how we have electricity in this building, right? You have to have a certain energy to push those electrons in a certain circuit or the system. So you can have this type of energy. So we can put it on the light energy or some of the energy to use our device in there. Okay? So this is obviously one type of a kinetic energy here. Tricky one is this one, the heat energy. What is a heat energy, by the way? So here's the thing. If you try to touch something that is really hot, like it has really, really hot, like a metal ball, like this was on stove for like hours. If you try to touch it with your fingers, what do you feel? If you touch something really, really hot what do you feel? You feel pain. Perfect. Thank you. So why you feel pain? That's the question. It's not bio class. I'm asking you why you feel pain when you touch something hot. Because it goes on your some action on your hand. You have some biological, the answer for it, which is the neural kind of receptors, the stimulus from the outside and transmit it to central nervous system. But actually what happens is something really hot means it's very high in heat energy, right? That's what it means. But the heat is kind of a transformable kinetic energy. So if you have something that is really hot, what happened to that matter or any object is they're going to have a very high. Okay, show you the. So you give a very high in heat energy. Okay, that can easily cause very high in kinetic energy. So your heat energy will transforming into kinetic energy. So easy. That's why if you touch something that is really hot, you'll feel pain because if you have a lot of molecules on your hand, having a really high energy as a kinetic energy, your hand will decompose, meaning it's burning out, right? The burning out simply means all the atoms in your hand will just leave because they're very high in kinetic, they'll just move. So this is why heat is a good example of kinetic energy. It can be easily transformed into the kinetic energy. So this is why our body is designed for not to touch something hot. That is best sign for your survival. So that's how your nervous system evolves. Okay, makes sense, right? Does it make sense? All right. So if that is the case, this is also kinetic energy. The light energy, obviously the kinetic energy. You have a lot of motions of the electrons or protons or upper particle, or especially at least the photon, will actually travel through the space. So you can have energy in form of a light, which might be something where we really appreciate because we get this energy from where? Sun. So if this one, we would have been surviving not even 1 single second. So this will be the all kinetic energy. It's good here. So how about the potential energy? So potential energy mainly two. It's nuclear energy, and the other one is a chemical energy. So nuclear simply means if you look at the nucleus of the atoms or the molecule, it all made by what? It's neutrons and protons and everything. But I'm not gonna go into very deep for nuclear energy because there will be too much involvement of the physics. But anyway, because of the maintaining something positive and negative and outside, they should have a certain great amount of energy to holding the position. Because okay, just forget what I'm gonna say just for 1 minute. But so to be the matter is almost same as energy. Because we don't know why, but to be matter, they need to have energy because they actually origin from the energy. That's how we believe. So to sustain this position over here, they cause really high energy to make this electron this position and to keep this positively charged protons in the center so strongly so they don't just decay. Okay? To do that, it will be lots of energy to keep this form, right? Because the matter is technically speaking from the high dense energy. If you know Einstein, you know Einstein. So I'm not gonna go in very deep. If you wanna know, you can stop by my office. But this is why it's potential energy, because it's caused by this position and how they try to manage the position of the things in the nucleus and even outside. Okay. Kind of makes sense, okay? But just so chemical energy is also type of thing. So whenever you think about some chemical bond formation, this is normally caused by either what electrical force or the sharing the covalent bond, covalent electron together in a certain reason here. So to make that happen, you need to have a certain amount of energy. This is why when the molecule is making a new chemical bond, they release the energy. If they break apart, you need to use energy to break it. Okay, so this is type of potentially you can use in the chemical reactions, and it's also caused by the position of in that the compounds of the molecule. So this is also potential. Kind of makes sense. You guys are any taking bio class? Anyone taking bio class? You guys know what this is, right? ATP? Yeah, this is a good example of chemical. Okay. So you can potentially keeping the energy in form of ATP, and later whenever you use muscle or your biometabolism here, all the kinetic energy is coming from potential energy originally stored in your compound in ATP. Anyway, I'll just move on. So does it make sense? We good? Okay. So just move on. All right. So here's the thing. As you know, maybe kinetic energy might be quite okay, but the potential energy wise, it's really hard to estimate how much it is. It's just so hard to estimate or to analyze. So the internal energy here should be kinetic energy plus potential energy. But it is so hard to estimate, but it's something that we can do easily is change in energy. Okay, so we can actually have, so you possibly don't know how to measure the internal original energy here, but it will be easier to see the difference between the first energy and the last energy. So you only need to get the gap. That would be the easier. Okay, so if that is the case, what we normally do is the work plus heat energy. So this W stands for work. This is work. This Q stands for heat. Okay, and those two will determine, this might be the change in the energy of something that is our system. Okay, so I'll give you one example here. You have one system over here. So system is just a very small portion of the whole universe. So it could be one chemical reactions, a certain small volume, or in a cup, or in the classroom, or a very small portion of the universe, and everything else will be surrounding over here. So this is a system. We can say anything about everything else will be surroundings over here. And then let's try to say we put the heat energy about 100 joule. Okay, so the joule is the energy unit. So 1 joule is equal to making 1 meter per second faster of the 1 kilogram object. But anyway, this is a unit of energy unit. So let's say we have 100 joule amount of heat energy going into system. Okay, meaning you kind of putting the light on the subject where no matter how you do it, you're adding the heat energy into here. Then this will become obviously what? Plus 100 joules. Okay, 100 joules over here. And then maybe for work-wise, this is kind of tricky. If you have, so surrounding, meaning anything except the system, right? So it could be even me. So if I or somebody did the work to system, meaning this is the same as they got energy, because somebody did the work for the system. So meaning this is the same as system getting that amount of work energy into themselves. Okay? Does it kind of make sense? So maybe I said I did like a 100 joule amount of work for the system or to the system. Then you can also have a additional 100 joule here. Okay? So the change in your energy should be 200 joule by just doing this one. Okay? So this is easier for us to estimate. So because we putting the 100 joule amount of heat energy into the system, and we also did the 100 joule amount of work for the system, meaning the system getting the 100 joule amount of heat energy and also amount of that work into the system. So they get in total 200 energy joule at the end. So that minus the initial one should be the plus 200 joules. Make sense, right? Okay. So how about the other one? Okay, we say if system emits the heat energy, so there was about maybe 50 joule amount of heat energy were coming out from the system. Okay, and then also the system did a work to surroundings. Okay, so system actually did a work for the system. So for example, if you have some like a gas cylinder, if the system tried to push the cylinder, that means it's outside of their system. So they're doing a work to the outside, to surroundings. In this case, also maybe it's 50 joule. So if not the surrounding, but system doing the work for the surrounding, it's also same as it's losing energy, because to do that work, they need to have the energy, right? But they already did a work for the surrounding, meaning they already used that energy to surrounding. So they lost the energy, so it's a negative. So it's negative is from this view, right? For system, they lost energy. For surrounding, they gain energy. Okay. Same here. This is heat energy actually coming out from the system. So system is radiating the heat energy in 50 joule mod. Then it becomes negative as well. Okay. So in that case, the change in energy of the system will be what? Negative 50 joule. Negative 50 joule. Okay. So it will become negative 100. So meaning in overall, in terms of heat and the work, that your system lost 100 joule amount of energy. Yeah, go ahead.
Could you just explain one more time why it would be negative 50?
Yeah. So so this is because we estimating the change in energy of a system. Okay. So if for example, like you did a lot of work, right? If you did a lot of work, you feel tired because you lost energy to do the work. That's why it becomes negative for system, because system did a lot of work for surrounding, meaning the system will lose a lot of energy to do those work. So then it's negative. But in the previous one was actually plus, because the surrounding did a work for the system. So system didn't have to do anything, but the work has already been done by surrounding. So that is the same as system actually gained that amount of energy. That was why it was positive. But in here, system was the one actually did the work, so it's negative. So the heat is the same. So they actually try to emit the heat energy, meaning they also need to lose that amount of energy to make it release the heat. So that's why we're putting also the negative sign. But if we try to hit that system with some stove or the Bunsen burner or the sun, anything that comes in and heat energy going into the system, then you're gonna put the positive sign. Okay? And then just you need to add this work and heat, W and Q value together. That will be your change in your internal energy of the system. Make sense? Kind of make sense? Okay. So here's a tricky one. So in your exam, so I just say this one is negative maybe 100 joule here, right? For example, then I'm gonna say the system lost 100 joule. This would be wrong. Okay, so see your calculation says negative 100, right? Negative 50, negative 50. But if you choose this answer as your choice, it will be wrong because the lost has already negative sign meaning. So in this case, it has to be this one is right. So this is I know it's kind of tricky, but please be careful with the wordings. Okay, so your calculation says negative in total. That means the system lost that amount of positive energy, because the loss means negative. It's tricky, right? So be careful with that. Okay. I'll give you one example here. So can you guys do this real quick? So you have a system here, and I'm gonna say heat energy or going in from the surroundings. It was about 120 joule, okay? And the system did a work about 50 joule amount of work, did the work, okay? What might be the change in energy? Just 1 minute maybe. So the heat energy is going into the system now, and at the same time the system did a work that is about like a 50 joule amount of energy work. Okay. So I know how to do this 120, 50. Only thing you need to be careful is the sign for this one. And that is the kind of the key points. What sign you need to put in there. So in here, this will be plus or negative. Be plus, perfect, because it's going into the system. So system-wise, it will be plus. Okay, but system is now doing a work for the system, so it will be negative, perfect. So it will be 120 plus, but it's a negative, so it will be minus 50. Will be 1 plus 70. So in this case, the system gained the 70 joule amount of energy in total. Okay. Does it make sense? Can I move on? Okay. Good. Perfect. All right. So whenever we talked about the system and the surrounding here, there's a 3 systems I want you to remember. So the first one is open system. Open system simply means if you have a system here, you can exchange what you can change the matter and also the energy. So meaning you can put the heat energy into the system or take the heat energy out to the system. You can put something into the system. You can take something out from the system. We call open system. Okay, this is the first one. The second one is a closed system. So closed system is like a sealed bottle. If you have a sealed bottle, okay, like well, it could be any system. You cannot put anything into the sealed bottle because it's closed. You actually close the bottle. So nothing can go into the here, but you can still do heating, right? You can still heat the sealed bottle. So you can actually change the amount of the matter inside, but you can actually change the amount of the energy inside. by just heating it and cooling it, or put the light on it, okay. So this is a closed system. The last one is the isolated system. So the isolated system means probably you kind of can guess by looking at the first two. You cannot change the amount of the matter inside, and also energy neither. So you can do nothing to this system. It just system stay as that is. It is forever. So we call this isolated system. So good possible plausible example of this one would be like a thermal cup, like a styrofoam cup. It is not perfect for proving the energy going in and out, but it's somewhat better than all the regular bottles, right? So it's not perfect, but can you guys actually guess what might be the perfect example of isolated system? Nothing can go. Yeah, go ahead.
Like a vacuum?
Vacuum. Yes, very very good. But you can put something into vacuum though. Yeah. So I mean, but she's very close, because my answer to this one is very close to her answer, because it's a universe. So as you know, by its definition already, nothing can be outside of the universe, because universe means everything. So a universe might be the perfect example of, actually perfect only one example of isolated system, which we assume there's absolutely nothing outside. So you can either change the matter or the energy from the outside, because nothing out there. Yeah. This might be on your exam. Okay, anyway, so here's one thing I want to mention before I move on. Is the universe is really isolated system? Do you think? Is the universe is really isolated system? Do we know the endpoints of the universe? So what I just meant is observable universe, meaning we think we saw the part of the size or the endpoints of the universe, but we actually can't be sure. It's impossible to be sure, I think. But just in theory, that's the good example. So anyway, because they try to look at the trace of the light, they use a cosmetic spectrums and but we who knows? All right. So let's move on to the next one. So this is a kind of a tricky, but you can try to follow each step by step. You'll be able to get this one quite well, actually. So this is once again, it's stand for heat energy. So this is why I'm gonna put these numbers in joule, which is a unit for energy here, and there's a C times M times delta T. This is something I want you to memorize for the exam. So C stands for specific heat. The M stands for mass. Okay? And the delta T stands for change in temperature. Okay? So change in temperature simply means final temperature minus initial temperature. So I just put like a subscribe F here to make this final temperature. Initial temperature is I here. Okay? So I and F. Final temperature minus initial temperature will tell you the change in temperature, right? So this is what we mean delta T. So delta simply means change in something, and T stands for the temperature. That's why it represents the change in temperature. Okay, so this is how it. Next slide. Okay, so here's the thing. specific heat here is kind of tricky one. This is something require amount of energy to increase the temperature of something by 1 degree. If degree, the temperature, I'm gonna write the temperature of some matter that is 1 gram. Okay, so if there's a certain amount of energy to increase the temperature of 1 gram water by 1 degree, that would be the heat, specific heat for water. Okay, makes sense, right? So 1 gram of something, you try to increase the temperature by 1 degree, and you need that amount of energy, that is your specific heat. Okay, so for example, for water, you have about 4.2 joule per grams Celsius. So if you look at the unit here, it actually kind of makes sense. So it means you need to have about 4.2 joule amount of energy to increase the 1 gram of water. Maybe it was initially 20 Celsius degree in room temperature to 21. Then you need to have this amount of energy. That's what it means. Make sense, right? Okay. So if you have a 4.2 joule amount of energy, you can increase the temperature of the 1 gram water by 1 degree. Okay. So meaning, for example, if that is the 1 gram, that's the number. If what if we have 10 grams instead of 1? How much energy you need to have? You have to 10 times this number. That's why we multiplying this number by m, which is also in gram, mass unit. It makes sense, right? So, for example, if you need a 4 joule amount of energy to increase 1 degree of 1 gram, you have to have an 8 joule amount of energy to increase 2 grams of that by 1 degree. Right? So you can actually multiply that by the mass in grams. That will tell you how much energy is required there. But another thing is, if you want to increase the temperature not just by 1 degree, but maybe 10, then you also need to multiply that by change in temperature. That will give you heat energy to do so. Makes sense, right? Okay, so I don't know. I know you guys, most of you are 18 or 19, or 20. You guys know how old I am, right? I'm 36. When I was your age, I used to play a computer game. Not very much, a few times. Do you guys know the game named Diablo? I played the Diablo 3. There's a Diablo 3 is a role-playing game, RPG game. To get to the higher level, you need to finish the quest assigned from the system. And then here's my thing. There is a quest you need to finish, that is clean up the monsters on the top of mountain. And I memorized it like 20 years ago. I still remember it. No problem, because it's so in my mind. So just, I don't know what your weight is, try to remember this equation. This was on the exam. So try to find a way to memorize this one. But this is the reason why we're doing this one, to get the total heat energy to make it happen. Make sense, right? Okay, let's try to do the practical problems. And then maybe if you have time, but yeah, let's try to one. So for example, over here, if you have maybe 100 grams of water, okay? You have 100 grams of water. It's at room temperature. So room temperature normally 20 Celsius degree. Okay? And then I wanna make like a hot water. Okay, it's not like boiling, but somewhat warmer water than room temperature. So I wanted to like put it into the 40, which is quite warm and still kind of not so hot water. still is 100 grams over here, right? Then how much heat energy to make it happen is just like that. So the Q is still your heat energy in joule. And like I said, specific heat for the water is about 4.2 joule per Celsius and grams, okay? Or grams from, it doesn't matter which one goes first. But you have 100 grams, not 1 gram, right? So you have to multiply by 100 grams. Because you're not dealing with the 1 gram, but 100 grams. It has to be 100 times bigger. And now you have to get the change in temperature. So this is the temperature that you want your water like cutting up to. So then this will be your what? Final temperature that you're designing. Okay? And this is your initial temperature. Because this is water at this temperature. So once again, delta T is the same as what? Final temperature minus initial temperature. Okay? So you only need to plug those two numbers in here, which is 40 minus 20. Okay? Right? So if you do that, this is just literally 4.2 joule per Celsius times grams times 100 grams times 40 minus 20 is 20 Celsius degree. So you see those units cancel. Okay, you can get the numbers in joule. Okay, so that will be yeah. So this is the answer. Okay, so you need to have this amount of energy to make your 100 grams of water from 20 Celsius degree to 40, and you need to input this amount of heat energy into the water, so you can make that water going up to the 40 Celsius degree. Okay, makes sense, right? So let's try to do. Can you guys maybe try? I will just leave this one. Okay, maybe if on the exam, maybe I can say you have a water here. You have like 20 grams of water here. Initially was 20 Celsius degree, but you want to 30. Okay? Can you guys do this real quick? So it stay the same, right? Specifically the same, because the same water. You only need to change the gram and the delta T, which change in temperature. Okay, just 2 or 3 minutes, I guess, and then we'll move on to the extract code. Okay, so try to get the mass, and then try to get the change in temperature, and if you just multiply them all, you get the total heat energy is required. Okay? But 1 or 2 minutes, we'll do this together. Okay, 30 seconds. Okay, so this is 20 grams, right? So I'm gonna plug 20 grams over here. So we're assuming this will be our final temperature, so I'm going to switch this one to 30, and this is our initial temperature is 20. So this is the same as what? 10. Okay, so the answer will be am I right? Yeah, okay. So you need to have this amount of energy to make this happen, following this equation. Okay? So I'll just stop here today.